Hello, good morning everyone. Today we are going to discuss about the resting membrane potential. I myself, Prem Singh Chauhan, Associate Professor in Geology at St. Ranglal Kothari Government PG College, Rajsamand. As we know, electrical potential exists across the membrane, which virtually all cells of the body. Some cells such as the nerves and muscle cells generate rapidly changing electrochemical impulses at their membrane. And these impulses are used to transmit signals along the nerve or the muscle membrane. In another types of cells, such as glandular cells, macrophages, and ciliated cells, local changes in the membrane potentials also activate many of the cell's functions. The basic physics of the membrane potential is membrane potential caused by iron concentration. This is iron, not iron. First of all, we discuss about the membrane potential caused by the iron concentration, among which the first point is the differences across a selective permeable membrane. The potassium concentration is great inside a nerve fiber membranes but very low outside the membrane. Let us assume that the membrane is in the instance is permeable to the potassium ion but not to any other ions. Because of the large potassium concentration gradient from inside toward outside, there is a strong tendency for the extra number of potassium ions to diffuse outwards through the membrane. As they do so, they carry positive electrical charges to the outside, thus creating electropositivity outside the membrane and electronegativity inside because of negative anions that remains behind and do not diffuse outward with the potassium. Within a millisecond or so, the potential difference between the inside and outside, called the diffusion potential, becomes great enough to block further net potassium diffusion to the exterior. Despite the high potassium ion concentration gradient, the normal mammalian nerves fiber, the potential difference is about 94 millivolt with negativity inside the fiber membrane. The next section, in which the same phenomenon, but this time with a high concentration of sodium ion outside the membrane and a low concentration of the sodium ions inside. These ions are also positively charged. This time, the membrane is highly permeable to the sodium ions but is impermeable to the all other ions. Diffusion of the positively charged sodium ions to the inside create a membrane potential of the opposite polarity to that, with negativity outside and positivity inside. Again the membrane potential rise high enough within the milliseconds to block the further net diffusion of the sodium ions to the inside. However, this time the mammalian nerve fiber, the potential is about plus 61 millivolt inside the fiber. Thus, in both parts, that a concentration difference of the ions across a selective permeable membrane can, under appropriate condition, create a membrane potential. Second, the nearness equation describes the relation of diffusion potential to the ion concentration differences across a membrane. The diffusion potential level across a membrane that exactly opposes the net diffusion of a particular ions through the membrane is called the nearness potential for that ions, a term that was introduced. The magnitude of nearness potential is determined by the ratio of the concentration of the specific ions on the two sides of the membrane. The greater the ratio, the greater the tendency for the ions to diffuse in one direction, and therefore the greater is the nearness potential required to prevent additional net diffusion. The following equation, called the nearness equation, can be used to calculate the nearness potential for any univalent ions at the normal body temperature of 98.6 degree Fahrenheit. It means 37 degrees centigrade. The EMF effective in millivolts is equal to plus minus 61 upon Z multiplied by log concentration inside upon concentration outside. This is the formula through which we can calculate EMF in millivolts is electromotive force, where Z is the electrical charges of the ions, plus 1 for K plus. When using this formula, it is usually assumed that potential in the extracellular fluid outside the membrane remains at zero potential, and the nearest potential is potential inside the membrane. Also, the sign of potential is positive plus if the ions diffusing from the inside to the outside is a negative ion, and it is negative if the ions is positive. Thus, when the concentration of the positive potassium ions on the inside is 10 times, thus on the outside the logs of 10 is 1. So the near-net potential calculate to be minus 61 millivolt inside the membrane. The Goldman's equation is used to calculate the diffusion potential when the membrane is permeable to several different ions. The Boltzmann equation is used to calculate the diffusion potential when the membrane is permeable to several different ions. When membrane is permeable to several different ions, the diffusion potential that develops depends upon three factors. First, the polarity of the electrical charges of each ion. First, the polarity of electric charges of each ion. Second, the permeability. And third one is the concentration. Concentration of the respective ions on the inside and outside of the membrane. Thus, the following formula EMF is equal to minus 61 multiplied by log of concentration of the sodium ion and polarity of the electrical charges of the sodium ion upon concentration of sodium ion. यहाँ inside आएगा, ये inside है all, और इधर है outside. Same concentration of the sodium outside and P and A plus. Same is calculated with the C and P of the potassium ion, concentration of the potassium K plus ion upon, इधर भी प्लस होएगा, and plus concentration of chloride ion and concentration of the polarity of the potassium ion. This formula actually not to be written on this screen, so I can repeat it once again. The electromotive forces in millivolt is equal to minus 61 multiplied by log concentration of the sodium ion inside multiplied by permeability or the polarity of the potassium ion inside plus concentration of the potassium ion inside multiplied by permeability or the polarity of the potassium ion plus concentration of the chloride ion multiplied by permeability or polarity of the chloride ion inside upon concentration of the sodium ion multiplied by polarity of the sodium ion inside outside plus concentration of the potassium ion multiplied by permeability of the potassium ion outside plus concentration of the chloride ion multiplied by permeability of the chloride ion outside. So the several key points becomes evident that Boltzmann equation, first sodium, potassium and the chloride ions are the most important ions involved in the development of the membrane potential in the nerves and muscle fiber, as well as in the neuronal cells of the nervous system. The concentration gradient of each of these ions across the membrane helps determine the voltage of the membrane potential. Second, the quantitative importance of each of the ions in determining the voltage is proportional to the membrane permeability for the particular ions. That is, if the membrane has zero permeability to the potassium and chloride ions, the membrane potential becomes entirely dominated by the concentration gradient of the sodium ion alone, and the resulting potential will be equal to the nearness potential for the sodium. The same holds for each of the other two ions if the membrane should becomes selectively permeable for either one of them alone. Third, a positive ion concentration gradient from the inside the membrane to the outside causes electronegativity inside the membrane. The reason for this phenomenon is that excess positive ion diffuse to the outside when their concentration is higher inside than outside. This diffusion carries positive charges to the outside but leaves the non-diffusible negative anions on the inside, thus creating electronegativity on the inside. The opposite effect occurs when there is a gradient for a negative ions. That is, a chloride ion gradient from the outside to the inside causes negativity inside the cell because excess negatively charged chloride ion diffuse to the inside while leaving the non-diffusible positive ions on the outside. Now, how we can measure the membrane potential? The methods for the measuring of the membrane potential is very simple to say in the theory, but it is often difficult in practice because the small size of the most of the fibers. A small pipette filled with an electrolyte solution, the pipette impelled through the cell membrane to the interior of the cell fiber. Then another electrode called indifferent electrode Then another electrode called indifferent electrode is then placed in the extracellular, and the potential difference between the inside and the outside of the fiber is measured using appropriate voltmeter. Then the microelectrode is connected to an oscilloscope for recording rapid changes in the membrane potential during the transmission of the nerve impulse. The electrical potential that is measured in each point in or near the nerve fiber measure beginning at left side of the feet and passing to the right. As long as electrode is outside the nerve membrane, the recorded potential is zero. When is the potential of the extracellular fluid, then as recording electrode passes through the voltage changes area of the cell membrane called the electrical dipole layer, the potential decreases abruptly to the minus 90 millivolt. Moving across the center of the fiber, the potential remains at steady minus 90 millivolt level but reverts back to the zero the instant it passes through the membrane on the opposite side of the fiber. To create a negative potential inside the membrane, only enough positive ions to develop the electrical dipole layer at the membrane itself must be transported outward. All the remaining ions inside the nerve fiber can be both positive and negative. Therefore, transfer of an incredibly small number of ions through the membrane can establish the normal resting potential of minus 90 millivolt inside the nerve fiber, which means that only about 1 upon 30 lakhs to 1 upon 10 crore of the total positive charges inside the fiber must be transferred. Also, an equally small number of the positive ions moving from the outside to inside the fiber can reverse the potential from minus 90 millivolt to as much as plus 30 millivolt within the little as 1 upon 10,000th of the second. Rapid shifting of the ions in the manner causes the nerve signals dispute in subsequent section. The resting membrane potential of a neuron. Resting membrane potential of the large nerve fibers when they are not transmitting nerve signals is about minus 90 millivolt. That is the potential inside the fiber of the 90 millivolt more negative than the more potential in the extracellular fluid on the outside of the fiber. The transport properties of the resting membranes for the sodium and potassium and the factors that determines the level of these resting membrane potentials are explained in detail in next section. But what are the reasons behind resting membrane potentials? Are active transport of the sodium and potassium ions through the membranes and sodium potassium pump, and second one is the leakage of the potassium through the nerve cell membrane. We consider first active transport of the sodium potassium ions through the membrane, the sodium potassium pump. As we know, All about the sodium potassium pump. All the cell membranes of the body have a powerful sodium potassium pump that continually transports sodium ions to the outside of the cell and potassium ions to the inside. This is an electrogenic pump because more positive charges are pumped to the outside than to the inside. 3 sodium ions to the outside for each 2 potassium ions to the inside, leaving a net defect of the positive ions on the inside and causing a negative potential inside of the cell membrane. The sodium potassium pump also causes a large concentration gradient for the sodium potassium across the resting nerve membranes. These gradients are sodium plus outside is 142 milliequimoles per liter. Sodium inside is 14 milliequimoles per liter and potassium outside is 4 milliequal moles per liter and potassium inside are 140 milliequivoles per liter. The ratio of these two respective ions from inside to the outside as follow. Sodium inside is 14 and upon sodium outside is 142. It means 14 upon 142 is equal to 0.1. And for the potassium inside is 140 and upon potassium outside is 4. 140 upon 4 is equal to 35.0. The next reason comes leakage of the potassium through the nerve cell membrane. The channel proteins, sometimes called tandem pore domains. Tandem pore domains. These are the potassium channels which leaks potassium from these channels. In a nerve membrane through which potassium can leak even in the resting cell. These potassium leaking channels may also leak sodium ions slightly, but are far more permeable to the potassium than to the sodium. Normally about 100 times as permeable. This differential in the permeability is a key factor in determining the level of the normal resting membrane potential. Now we comes to the how resting membrane potential is originated in the normal cell. So the origin of the normal resting membrane potential. There are important factors in the establishment of the normal resting membrane potential is minus 90 millivolt and there are as follow. First, the contribution of the potassium diffusion potential, contribution of the sodium diffusion through the nerve membrane and contribution of the sodium potassium pump. First, we explain how the contribution of the potassium diffusion potential play important role in the formation of normal resting membrane potential. The only movement of the ions through the membrane is diffusion of the potassium ion by the open channels between the potassium symbol capers inside and outside of the membrane. Because the high ratio of potassium ions inside to the outside is equal to, now we calculate this is 35, so 35 is to 1. The nearest potential corresponding to this ratio is minus 94 millivolt because logarithm of the 35 is 1.54 which is multiplied by minus 61 millivolt and it becomes now is minus 94 millivolt. Therefore, if the potassium ions were the only factor causing the resting membrane potential, then the resting membrane potential inside the fiber would be equal to minus 94 millivolt. Now we come to the concentration of the sodium diffusion through the nerve membrane. Addition to a slight permeability of the nerve fibers to the sodium ion caused by the minute diffusion of the sodium ions through the potassium Na plus leak channels. the ratio of sodium ions from the inside to outside, which is we calculated earlier, which becomes 14 upon 142, it becomes 0.1, which is we calculated nearest potential for the inside of the membrane of plus 61 millivolt. Also, nearest potential for the potassium diffusion is minus 94 millivolt. How do these interact with each other? What will be summated potential? This question can be answered by the using Boltzmann's equation described in the next section. Instinctively, one can see if the membrane is highly permeable to the potassium but not as slightly permeable to the sodium, it is logical that the diffusion of the potassium contributes far more to the membrane potential that does the diffusion of the sodium in the normal nerve fiber. The permeability of the membrane to the potassium is about 100 times as great as its permeability to the sodium. Using this value in the Boltzmann equation gives a potential inside the membrane of minus 86 millivolt, which is near the potassium potential shown in the figure. Now we comes to concentration of the sodium potassium pump. Contribution of the sodium potassium pump is provide an additional contribution to the resting membrane potential. That there is a continuous pumping of the three sodium ions to the outside for each two potassium ions pumped to the inside of the membrane. The pumping of the more sodium ions The pumping of the more sodium ions to the outside, then pumping of the potassium ion to the inside, cause continuous loss of positive charge from inside the membrane, creating an additional degree of negativity about minus 4 millivolt additional on the inside beyond that, which can be accounted for by diffusion alone. Therefore, the net membrane potential when all these factors are operative at the same time is about minus 90 millivolt. In summarized way, we can say that diffusion potential alone caused by the potassium and sodium diffusion would give a membrane potential of about minus 86 millivolt, with almost all these being determined by potassium diffusion. An additional minus 4 millivolt is then contributed to the membrane potential by continuously acting electrogenic sodium potassium pump, giving a net difference potential of minus 90 millivolt. Impermeant anions Gibbs Donan phenomenon. Inside the cell are many negatively charged ions that cannot pass through the membrane channels. They include the anions of the potassium molecule and of many organic phosphate compounds and sulfate compounds. Because these ions cannot leave the interior of the cell, any defect of the positive ions inside the membrane leaves an excess of these impermeant anions. Therefore, these impermanent negative ions contribute to the negative charge inside the cell when there is a net defect of positively charged potassium ions and other positive ions. So, today we learn about the how the resting membrane potential of a nerve fiber acting upon the nerve fiber, and what is the contribution for the formation of the resting membrane potential of individual potassium ion, individual sodium ions, and role of sodium potassium pump. Thank you for watching this video, and we hope that this video becomes useful for you to learn about the resting membrane potential. Thank you once again.